Good evening, everyone. Myself, Chiranjeev Sarkar, Vice Chair, Tunnel Association India Young Member Group. So we welcome you on today's webinar, WBR 33, on title Value Proposition and Sustainability of the TBM Tunneling by Mr. Gaspari. So we welcome Mr. Gaspari. About Mr. Gaspari, Mr. Gaspari is Vice President Tunnel Practice Lead of Canada, US East and Latin America. He has 17 years of experience in tunneling industry in transportation, water and power industry in Europe, Asia and America. His experience covers all project phases from conceptual development to preliminary detailed design into implementation, both in the traditional design and build contract and alternative delivery procurement, including design and build and P3. He held various roles as a tunnel technical leader, design manager, project manager. His expertise include design of tunnel excavated in the both conventional and mechanical method, design of tunnel and underground caverns for hydropower plant, tunnel portal, cross passage, design of curtain cover station, both for top-down and bottom-up concept, design of construction and management of the TBM tunnel, both for EPB and slurry cell, including parameter settings, multi-criteria analysis, developing plan for tunnel achievement in both building risk assessment plans. Mr. Gaspari has actively engaged in tunnel professional community for about 20 years. He started collaborating during his early degrees with Professor Rikabi and Pazila on the mining project. He developed technical and commercial skill working on some world largest and complex underground project across 3 different continents, residing 8 years in America, 7 years in Asia, and rest in the Europe. He is currently youngest ever working group chair of International Tunneling Association, ITIATS. He gives backs to the community, volunteering to the lecture at the top university and training courses. So over to you, sir. You can start your session.
This was a massive introduction. Thank you very much for it. But I hope I can live up to what you said. Thanks a lot for the invite. I'm always happy every year to come back to India digitally. You know, I spent 5 years of my life between Bangalore, Delhi, and Mumbai. So India stays in my heart all the time. So let's get started. Today, I want to try to identify some of the case histories that apply the best to some of the recent work we're doing in the International Tunneling Association around the value proposition of TBM tunnels and the sustainability aspects of them. So let me try to go presentation mode and confirm if you can see the full screen, right? Can you?
Yes, sir.
Let me minimize this face. So you already introduced myself. Let's not waste time. The agenda for today, I hope I can cover it all, is starting from an understanding of the value proposition of tunneling. We will work into some thematic case histories. In particular, you know, facing the geological and geotechnical challenging is always the first point. We will try to look at some examples of how to mitigate the impact on existing structures, and then existing and future solution about break-in and break-out, and then some unforeseen accidents that I'd like to show to you. So please do not record. Oh no, you're recording this meeting.
Yes,
but
sir.
it's okay.
Recording is on.
I'll moderate my language then.
Later on,
And
actually, this video will be available in the YouTube channel also.
no problem. That's fantastic. Thank you a lot for confirming that. But it's always good to learn about those experiences. So in general, you know, there has been some studies and a report here, some by Alun Thomas presented last year as part of our International Tunneling Association World Tunnel Congress that look after the life cycle analysis for the sustainability of TBM tunnel. And the good news is that really there is a lot of action going on, particularly between the production and the construction to reduce the carbon footprint of materials, but also of the operations that are in our tunnels. So as you may notice here, the concrete, either secondary or primary lining, is the biggest element introducing carbon issues in our project, and acting on that is actually our target to try to reduce the carbon footprint of our tunnels. As a kind of a test run in working group 20 together with the ITATEC committee, we have taken the studies from Arun Thomas and moved to a group that is currently analyzing what could be the impact of adjusting also the design of some of our tunnels to reduce the impact of concrete by different type of fibers. You may notice here that the concrete is still the biggest element, but if you start moving in from rebar to steel fibers to microsynthetic fibers, you may actually obtain a reduction of the overall carbon footprint and even an increase of durability. Now, the next target is try to reduce the concrete amount itself, and there are some design solutions that can help on this one. In terms of value proposition of tunnels, they host several elements, either roadways or railways or underground lines, different diameter of tunnels for different type of use. That is pretty well known. But what is currently not well framed is the risk matrix around the overall lifetime of those tunnels. And you may notice that I try to identify here some developing frameworks from the organization and governance, which establish the planning of a tunnel, into the procurement of those through supplier versus buyer power, and then the economical impact of those projects that sometimes can be delayed, leading to escalations, and then sometimes may have side issues or unforeseen risks that may deal with contingency. Finally, the aspect that we usually work more on is the one of the execution with investigation, design, and then the construction itself. And finally, the operation and maintenance. So if you try to frame your project within those different phases, and at the same time, those macro areas, and as you notice, I divided in 4 corners: market, management, execution, and social aspects. You may actually have a better organization of what are the overall risks and opportunities that you want to consider when you work on a tunneling project. Moving into some of the interesting examples, one of the ones that that was developed years ago in Canada is this Southeast Collector. And a throughout study in 2003 was already conducted as part of the environmental assessment on the carbon footprint of those tunnels. And particularly, what was calculated is not only the impact of the negative impact of construction, but also the positive impact that may rebalance the carbon footprint through the advantages of better dealing with all of the CSO water in this area. So quite interesting to always consider those elements in a holistic approach. In that case, a comparison between different cost items was run, and also the identification of the solution that was faster and cheaper, and at the same time with less environmental impact was considered. So you may notice here an open cut or cut and cover compared with the TBM tunneling. And TBM tunneling was preferred at the end of the game, not only because it represented a less risky construction method at some locations, particularly where we got to underpass highways or railways, but particularly with the considerations of less environmental impacts. As we all know, an open cut may be more dangerous also for the local environment. So this is just an example, but I want to start focusing more on the typical aspect of the geological and geotechnical challenges. And I want to stay in Toronto, and I want to stay in York region here in Canada, where another project is currently under tendering position right now, which is the West Vaughan Sewer System project. These are all the presentations from York region. I pay credit to them, and they presented also an interesting study to optimize a concept alignment and a concept design, including open cuts and micro tunneling, and moving these into larger TBM tunneling to try to both reduce the number of compounds, the social disruption that they represented, and the number of shafts that would have actually increased the environmental risks overall. And this is a typical little fish, the red diesel that was found in the local rivers, that is a species at risk and needed to be protected. And by reducing the surface impact of the project and moving more into tunneling, it was achieved a better preservation of this species. Definitely one important impact is by the procurement method. When we move from a prescriptive design to a performance-based design, we always have to consider that um, we increase progressively the complexity, the number of stakeholders and the interactions, but at the same time, we also increase the risk transfer from the owners to the contractors, allowing at the same time simplified construction management, involvement of new technologies, and really letting the contractor expressing themselves with their consultants and their engineers to deliver what they're best in delivering. So I, I do believe this is another important factor when we evaluate tunneling projects, because not only the technical aspect but also the commercial aspects needs to be considered to allow those new technologies, for example, those carbon um, footprint reduced materials to be implemented. And an example of the West phone is a good one, because again, in this case, different type of TBMs were adopted, a number of maintenance shafts were considered. Now, this may not be the final solution that will be used. This was an old presentation that was given to the Tunneling Association of Canada. But you may notice that the organization of a contract and the preliminary identification of TBMs that were to excavate in rock versus TBM that were to excavate in soil, respectively in red and blue, was helping to identify also disconnecting shafts from one to another construction solution. The geological risks were different in soil and rock. Particularly, rock masses were characterized by shale, potentially swelling, and the soils, glacial tilts in general, may add some sandy pockets, some gravel and boulders that could have represented a hazard for effective TBM tunneling. Uh, Not only you have to collect the potential hazards in tunneling, but you have to try to understand what those hazards are causing in terms of impact on your construction methodology. In this case, loose grounds, erratic boulders, or the high geovariability led us to think that a mixed phase solution, a mixed phase could have been a challenge for tunneling, and that's why a closed mode TBM was to be preferred. The closed mode TBM was also the conclusion of potential larger water inflows that you see from the central bucket coming out of pressurized aquifers or local peat and swamps, but at the same time also for resolving through the introduction of potential slurry, the isostatic readjustment, the glaciotectonic processes, and some faulting that could have created sticky behavior on the material that was extracted. So in that case, the risk register included all of that and came to the conclusion that, again, a TBM tunneling was favorable with respect to a micro tunneling that may have risk to increase the number of shafts per tier at certain locations that were challenging for environmental aspects. And the key point that was achieved was to organize the project with an increasing amount of geotechnical information to provide an initial geotechnical reference model, which would have then progressively improved as the phases of geotechnical investigations proceeded. And with such improved geological geotechnical reference model, a definition of TBS specs as well as the GDR could have been lined out. There is always a limit about the number of additional advantages you may have by increasing the number of geotechnical investigations. And that's why I always tend to remind that we have to be careful about where do we improve our phase 2 and phase 3 geotechnical investigations to make sure that we have the right inputs we need for our design. This was the final resolution of our risks. Through a risk register, we quantified risks that were at an unacceptable level, and we needed to mitigate them, and risks that instead were already at an acceptable level, so we didn't need to mitigate them. Mitigations were of different strategy of different type, accordingly with the type of category of those hazards. Health and safety hazards, with respect to environmental ones or constructions, were dealt in different ways. Some of the Potential mitigations included adoption of new technologies such as the gasket arrangement through you notice here the embedded gasket in the segmental lining, but at the same time, it's also analysis of ground reaction curve impact at the sidewalls different than at the crown, thus inducing potential differential movement within the rings and the segments there. You may notice that shale may swell, but can also be impacted by those subhorizontal layers of limestone that create localized additional stiffness and thus affect not only the construction of the tunnels, but also the segmental lining installation and stability, for which you need to add those circumferential joints and longitudinal connections through bolts. In this case, the longitudinal connection with bolts were decided to be excluded and substituted with typical guiding rods because in a lot of recent projects locally, it has been identified that the swelling is actually a movement that happens quite quickly during the excavation of the machine, but then it has a slow progression in time. So the installation would have not been affected by it, and guiding rods were enough to guarantee that perfect installation. At some other locations, geomitigations considered also the opportunity of using ground improvement, or even in this case, deepening the alignment to avoid the risk of water inflows. As you may notice, under a river, we got 5 meters of cover, and then it was increased to 8 meters of cover to allow for extra safety and reduce the risk of frack out on the surface. Not only design solutions, but also construction methodology and definition of construction sequences can help us mitigating some risks of the tunnels and increase the interest of using TBM tunnels respect to cut and cover or open cut approaches. In this case, different options were studied, and still the definition will be left to the contractor, but the initial study acknowledged the efficiency of starting from shaft number 7 excavated to shaft number 6, and using also shaft number 5 and number 2 as launching points respect to other solutions that you notice here. Another example that is quite interesting is an old study that was done for Spasskaya. It's a station in the middle of St. Petersburg, and you may notice here an intersection of a number of subways that were not properly efficient in terms of allowing people to get in and out. So an additional shaft to create an additional entrance was planned in a very dense urbanized environment. So a block was tarred down, as you notice on the right picture, and then inclined tunnels was supposed to connect to the station that was under the streets instead. This was reducing a little bit the impact on the social disruption due to utilities and traffic rearrangements during construction, but triggered some complicated design for the inclined tunnel. The face support pressure at a TBM bulkhead and the tunneling-induced settlements were properly calibrated to understand what would have been the impact on these underground services and reduce in this way the relocation of the TBMs, the relocation of the utilities, sorry. You see here the study that was done through a, excuse me, through a TBM, through a 3D modeling in FLAC that considered the presence of a TBM shield, the face support pressure on the front, the injection pressure in the back, and then the installation of the segmental lining in red. You may notice that a series of grounding consolidations were necessary in order to allow for a stabilization of the initial excavation steps from the launching shaft. And the face pressure was calibrated by studying different analytical solutions, as you see below. However, the numerical modeling, as you notice here, was the one that gave us the real decision over what type of face pressure to apply. And as you see, this is a very old FLAC model. Now, resolution is much better in the new models. But it was quite interesting to notice that due to the geological stratification and due to the fact that at deeper conditions you may add higher stresses, we increased the displacement. You see the blues and the reds in the right-hand images. But then after a certain depth, due to the different type of geology and the higher low in situ stresses, we stabilized the deformations, and actually they started reducing a lot. Consequently, face pressures needed to adapt to avoid that excessive face pressures may have actually caused heave on the top. So if you increase the face pressures as you go down, thinking that the more water, the more soil pressure, the more you have to push your face pressure ahead of your cutter head, well, you're doing probably a mistake. In fact, instead of doing the blue arrangement here, we decided to push with the red one, reducing progressively the face pressures as we're going deeper. Let's move into another type of mitigation now, which is the one of reducing the impact on existing structures. This is a case that comes from the Bangalore Metro. And I don't have to describe to you where is Bangalore and anything about it, but it was the garden city, the green city. So we got a lot of protests when we had to cut down some trees. I agreed with some of the protesters at one point, and we tried to reduce the number of trees to be cut. But that's just to give you an idea of how socially sensitive the city downtown was, as we were building 3 new stations and 6 kilometers of tunnels underground there. It was interesting to study the impact on some of the most important heritage buildings in the downtown area through both analytical solutions of the critical and standard scenarios on the left and numerical modeling to understand what was the impact of the different phase loss and soil deformation around the tunnel. And you notice on the right-hand side, most of you have studied already the Barland and Boscardin encoding solutions for the risk on buildings. So I'm not going to go in detail on that one. But according to the flexural or shear deformation of the buildings, a different risk category was assigned to each building, which you see on the bottom right image, concluding with the coloring red to yellow to green, according with the level of risk that we envisioned. Some of the structures, such as this temple, were pretty at risk. And in this case, particularly because you notice on the bottom left image, we were close to a station. So not only there were settlements coming from the TBM excavation, but also settlements from the deformation of the support of excavation of the station. Combination of the two led to these very high settlements that you see in red. Consequently, the deformation of the buildings were very high, and the risk of the brick masonry to crack and collapse possibly was to be resolved. Solution were mainly propping, as you noticed, or contingency plan. There are you guys know how important pujas are, and we needed to keep the temple open, at least some entrances, with respect to the main one, were alternatively kept open to make sure that the religious celebrations could have happened. This is where the temple was located. While we were caring a lot about the temple, on the other side of the streets, we started looking at some cracks. But sometimes it's difficult to understand if those cracks are induced by actually your tunnel solution or if they are readjustment of the foundation system, like in this case. So throughout studying of the pressures and injections on the face, we were able to identify that there was no connection with our TBM tunneling there. An older problem that I want to show you was to understand how much your mitigation measures are really helping you and how much instead they may create more damages. This is an old case for the TAIym Metro, where perforations due to a pillar consolidation to reduce the settlements induced by this single bore tunnel on an existing building that you see below were actually proven to be the cause of some extra settlements on the building itself. And this was done through back analysis, modeling that jet grouting consolidation, and identifying that actually the tension limit would have never been reached by the tunneling itself. There was no way whatsoever that we could have reproduced with existing available theories the very strange profile that you see on the bottom left corner here of deformations that were obtained. So some analyses were conducted to study and combine the tunnel induced settlements with the induced settlements from the drilling and injection of the grouting. And as you may notice here, actually, if you look at the red monitoring data, once additional injections were caused, a consequent heave was obtained and a resolution of the extra settlements was achieved, confirming one more time how important was the fact that proper injections were achieved and a reduction of the deformation during the drilling of the grouting solution would have actually avoided that extra settlements and cracks development on the building. Finally, an example on the São Paulo Metro here, which was a very important project run by the company that I was working for before. This is also an old publication that was run by the company. And sorry, apologies again. Different type of soils were encountered at different locations, including tertiary sediments and Precambrian bedrock. Different methodology were used as top-down and bottom-up methodologies. But what is interesting here is actually the intersection with the existing stations and how this was achieved through the use of TAIym tunneling underground. You may notice here, and this publication from the company at the time was called Geodata Engineering. That's the one that worked on these projects, and currently in the market as a name of Pini. The idea that they developed was the one of using these 3D intersections, and actually the use of these secant circular shafts intersecting with each other. With those large beams that were supposed to take into account the compression that was coming out of this arch effect and transform it into a very symmetric equilibrium condition for the structural loads. Now, one of the most risky situations that we need to deal with are actually the break-in and the breakout. And I want to look at here at some of these solutions. Now, this is a slide that comes from our colleague, Engineer Della Valle, who very clearly identify here what are the different risks of breaking in so basically launching a TBM. Okay, so to be more clear, when the TBM starts from a station box and starts excavating, you may notice that there are a number of risks for water to come into because the ring is not yet installed in the soil, so you cannot actually grout between the ring and the soil, and you have no guarantee that water inflows doesn't happen. So that's why you usually need a jet grouting block on the left-hand side, or you need into the station box a sealant ring, or maybe a combination of the two. On the right-hand side, when you have a breakout, so when the TBM comes into the station box, similar risks of water inflow and similar solution is applied of having a jet grouting block on the other end, as it is confining and reducing the risk of water to get in. And the jet grouting block is usually the length of the ring plus a couple of the length of the shield plus a couple of rings. So to make sure that you have enough of the grout that you see in brown here injected behind your rings. This is another the example that comes from the Bangalore project I was working on some years ago, where a sealant ring was chosen, as you notice, and embedded within a head wall to allow for the break-in, so for the launching of the machine. There was a shuttering pipe that allowed the sealant ring to be installed, as you notice here, and those gaskets were allowing for the water to stop coming into the tunnel should this being the problem. However, not always we were able to implement those solutions. And for the breakout, I told you a jet grouting block is usually favored. But if you have an existing building, as you see on the top, and you cannot drill around it, then you have no other solution than putting the same safety block inside the station. So in this case, we use this solution, again, as I mentioned before, TBM shield and 2 rings in length. The TBM would have come into the station from this direction. We had calculated the TBM thrust breaking into the station, and then the risk for the block to move away. Another loading conditions we consider is the one of the water around the shield of the machine when the shield is into the block. This water is hydrostatic with pressure in all directions, will induce some tension, as you see here, into the block, and consequently needed to be reinforced, as you see by those black lines, which are wire meshes. So the block was executed into the station while the station was excavated to prepare for the TBM arrival. When the block was completed, the first TBM on the left-hand side started pushing into the machine. You see some water coming out. That's the water that was trapped into the block. But luckily, the water at one point stopped as the machine broke through, and no additional water came through because that block was long enough to allow for sufficient length, and there were 2 rings that were having a safe back component grout injected around to guarantee full water tightness. Newspaper were happy about that, and then the second TBM also broke through in nearby. So that's an interesting solution to allow you braking into a station when you don't have the opportunity for jag grouting block outside of the station. The only problem is that then you have to demolish it, all of this amount of concrete. And as I said at the beginning, concrete is the highest carbon footprint. So I'm not definitely in favor of this being the right solution if you have an alternative to that. Also, the concrete has to be done in a low resistance one. In this case, they didn't use a low resistance concrete, so it took a little bit more time to demolish the whole block. But then it was done, and finally the station was completed. Another solution you can do to break out in a station is actually that of flowing the shaft. So you don't have to care about water inflow anymore. You know, in some cases like this in NEBT was done in Washington, D.C. in the United States, but also in Poland, as you see here, courtesy of Por and Gulemark. You know, some cases shaft flowed. So these were videos coming from a project in Brazil. That was not intentional, definitely. That's probably not even caused by definitely not. There was not water in the soil. That was caused by a damaged sewer in the vicinity of the station there. Now the break-in through a starter tunnel, it's an interesting solution. This one also in DC waters, again designed by Pini, is an interesting reference that has been published a few years ago. But also the Bergen Point, also this one was developed by Sally together with Posilico and with their engineering consulting firms, was an idea to actually put together a segmental lining with a conventional jacking frame that you would use on a micro tunneling. Now it was pretty large, but still possible. You know, 3 meter in diameter. The interesting point was that you needed to design, and that was where the designers were challenged in a transition piece between the segmental lining and the precast pipe lining. As you may notice, you know, 3D numerical modeling were adopted to design it. But what is interesting is actually the technology here and the way that the machine was designed to install the segmental lining, but also to be pushed in. Very smart idea and very interesting solution, as you see here, for a safe break-in. In Roma, a few years ago for the Metro C, Herakne developed this special cup that allowed to protect from water inflows. And now many other companies can provide a similar solution. It's kind of a real cap that you see there is a pressure release pipe at the bottom that allow you to reduce the pressure as the machine comes in. And once you release the whole pressure and you inject grout behind to completely seal the machine, it's a good solution to limit the amount of grout that you have to use. And grout is cement, as I said at the beginning. That is where we got the most carbon footprint of our projects. Other ideas comes from Paris, and these are from a Eiffage project in which they enlarge that cap to host the whole shield. It's kind of the concrete block that I showed before, but in this case is made of steel and may reduce actually the whole carbon footprint if the steel can be reused. It's not a new idea. It was done already in China. This is from CRTC. It's one of the projects in China, both break-in and break-out actually. An interesting new solution that has been done in Singapore in the DTSS tunnel from Leighton and Octave is actually that of not pushing through a pushing frame the machine as it starts, but to pull it to a flying launch solution, which has those cables that pull the machine against the soil, first against the support of excavation and against the soil. And it proved to be quite efficient, particularly if you have limited space, as you notice here, and you cannot push against the other side of the shaft. Do we have time for some unforeseen accidents? Actually, a couple of minutes here. Let me at least show you the first one on the Brenner, and then I want to give space for questions. I don't think we have time to look at everything here. The Brenner-based tunnel is this tunnel that connects Europe north to south between Austria and Italy. What was interesting here is that a exploratory tunnel between the two main tunnels was designed in order to provide geological, geotechnical information in a very uncertain geology. As you know, we are under the Alps, sometimes more than 1,000 meters of rock above you, and it's not easy to conduct an extensive geotechnical campaign, particularly not easy to drill boreholes, right? So that's why the exploratory tunnel was really a long borehole underneath the two future tunnels. And it was a useful one because then in the long term, it will be adopted as a safety exit and also as a service tunnel for cables and services to move from one side to another of the Alps. The section I worked on, which was quite interesting, was the one close to the Italian border in Fortezza. The exploratory tunnel was running through this granite of Bressanon, just before south of the Periadriatic Fault. You notice here the configuration of the mountains, the portal in Ica, and then the whole excavation. This was another interesting project that was run by Pizzarotti as a general contractor, and Sally was managing the machine and all of the team inside the tunnel. The diameter of the tunnel was 6.35 meters, so quite a large one for an exploratory tunnel, but that's why, because it was used also in future. So one of the accidents that happened here was a series of cracks developing on the sidewall. And there was no problem either in the design or the construction because everything was run as per standard. So the geology was not showing anything particular in this location. So when further investigations were done, after the tunnel face was stable, the opposite side of the tunnel was stable, a very strong granite, but the movement were strong and even the base was actually moving a lot. The backup was strongly deformed, as you notice here. So those studies actually, through drilling and testing, were showing this interesting parallel fault, subparallel fault that was not initially identified during the geological analysis. And the rock was pretty weak, very much with a very low RQD, as you may notice from this recovery here. Crashed completely. And so the accident, that's the lesson learned for me, is first of all to always consider the fact that there may be risks. And I'm glad that both the owner and the contractor in this case agreed on moving ahead with a fully shielded machine. Even if a granite could have been excavated by an open machine, the fact that we were fully shielded was actually helping in terms of safety. Because that accident would have caused a lot more problems if it was an open machine. However, the machine never performed as well as before, as you may notice, from some analyses that were run by me at the time that I was doing my thesis on this tunnel. And even if a double shield would have performed a lot better, these are on the right-hand side, some studies that follow research done by Grandori in the past few decades. Unfortunately, independently from the type of rock, the average rate of advance never reached the values that were possible before the big stop, right? So these were some of the results also in terms of the efficiency of the machine and the maintenances. So there were a lot of extraordinary maintenances that were not done before the accident, and ordinary maintenance also took a lot more time. So definitely an accident that created trouble to the possibility of maintaining the schedule. But again, it was an exploratory tunnel, so that was its purpose, to identify whatever was not possible to be detected from the outcrops. And these were some of the analyses that I published some years ago related to the different classes of rock and the correlations with the RME from Benyaski. It's an index that allow you to try to correlate the theoretical rate of advance with the quality of the rock excavability. But again, correlations were very weak because of those issues with the machine. So let me stop here because there is a number of other things I may tell you, but I want to grab some of the questions before it's too late, and I don't see your faces, so I don't see if somebody's sleeping or not here. Why don't I stop sharing and I give this 10 minutes for questions. Hello, can you hear me, Sakra?
Yeah. Thank you, Mr. Gaspari, for your wonderful webinar on TBM tunneling. I'm sure that your experience will be very useful to everyone present in this webinar. and also our student member have got a very clear idea about today's webinar. So now we will move to the question answer session. So now forum is open for any question. You can text or you can ask directly here. We will moderate the same. So any question? Yeah, Mr. Mike. Yes, Mr. Mike, please.
Good afternoon, everyone, and good morning, Giuseppe. I would like to make you a question, but thank you for sharing this, what you have given to us, particularly interesting, the break-in and breakout design options for the TBM. And in particularly, I enjoyed the first project and the different working methodology options for the two TBMs from the three different charts, because it gives these young members the right opportunity to understand what is the entire design making process, the brainstorm from the design perspective to actually launch a tender documents. But my question for you is on the carbon footprint reduction, because as we know, the ITA has launched an extensive campaign the last couple of years in reducing the CO2 carbon footprint emission in the tunneling industry. But I would like to hear your opinion on this, because much has been said, but in my personal opinion, not much has been done in a practical sense on the side. I would like to hear your voice, to hear your opinion, what you think about this, the status of things on CO2 emission reduction. Thank you so much.
Thanks, Mike. That's a great question, actually, because allows me to give some light over that initiative from ITA. I would kind of gently disagree that nothing has been done, because the industry, and you represent a good chunk of the industry as well, has been progressing with a lot of analysis, a lot of studies. ITA is trying to collect those studies and analysis and try to frame them within a universally accepted index for sustainability of underground structures that definitely needs to tap into the experience of our suppliers and our contractors and our designers. Now, what I can update you on, and Mr. Arnold Dix, our president, recently visited India and Tunneling Association of India, so he mentioned that as well in his visit, is that a committee has been created that collects all of the leaders of the working groups of ITA, including myself as urban tunneling working group leader, and a chair has been elected just 2 weeks ago, with 3 vice chairs. I am honored to be one of the 3 vice chairs of this special sustainability initiative of ITA. We have a task, which is by 2024, providing that draft index framework for the ITA working groups and member nations to review and possibly approve, and shed some light, hopefully, on the industry to identify what are the critical aspects we want to consider to make a tunnel really sustainable. Again, it has just started, and that doesn't mean that ITA, not having already framed that, no work has been executed, because again, the work of ITA is actually work that we do in our daily life, in our projects, and in our research and development. So that's what is currently going on, and that's what is the target. But I'm probably not the right person to speak about that. I am just referring what our president has mentioned recently in some of the meetings.
All right, thank you very much.
And thanks for the support of all the industry, because we can only do that if you guys continue to be passionate and invest in that.
Of course, and we need to transfer this to the youngsters.
Yes, absolutely.
There is one question in the chat box that request if you can cover the Bangalore Metro failure learning in the brief, as we don't seem to have many questions.
I was planning to do that, guys. I know, and that is another interesting story. So let me finish with that. It's another important lesson learned. Let me share my screen again. Oh my God, sorry, I was sharing only to myself. Oh, first, Nimal, is there a question from him? As I share my screen.
I think Sandeep have also one question. Sandeep,
Oh, Sandeep. Hi, Sandeep. Did it? Sandeep, do you have a question or?
Hi,
Oh.
hi, Giuseppe. Yeah, hi. I was just looking at one of the shaft options that you mentioned with the different rings coming together, and it looks a really nice solution where we can optimize the stresses. There was any study done to compare how much benefit we get from this option with respect to a conventional rectangular box uh, in terms of materials used? Or
Yes, those studies were done. Unfortunately, I'm no longer working with a company that developed them. It was Geodata, and now it's called Pini. They've done those comparison. I don't believe they've published that, so I cannot give you the numbers. I can only report on past projects through what was published already as a main of teaching, right? Because we're with young members here. But they were done comparison, and it was extremely advantageous to move from a typical concrete to an arched shape. You can think about yourself, like about how much bending moment you reduce by transforming everything in an arch impact, and also in an interaction diagram. If you increase the compression, you get in a much safer area, so you can allow for a lot more bending moment with the same amount of concrete. So you really make this concrete working much better. The problem we have with rectangular shapes is that like every beam, and they have a very high bending moment and very small normal forces, so the concrete really doesn't perform so well. But underground we cannot use just steel, right? And also steel has a large carbon footprint. But so that's the idea, like increase your normal forces, reduce your bending moments, and you'll get, I cannot say you what percentage, but there were an incredibly high savings on that. But I can put everybody who's interested in contact who with the designers and with that firm, so maybe they can disclose some information privately. And we definitely engage them probably in ITA working group, so they can give to us. Thank you, Sandeep. I'll use 1 minute to present you this story of this accident. If there are no more questions, it's interesting. It was a same project that we spoke before under different situation. Is the Bangalore Metro. It's a saprolite condition. So you have this very strong rock that through external agent has been progressively fractured, with water floods and high abrasive actions. So the bedrock weathering was really the key factor. This intermediate blue layer of mixed soil and rock, and then on the top you have a red laterite with fine loamy clay sands. But your TBM here, the TBM was running across both, so very challenging to find the right configuration of the discounters, the right type of materials to be used, moving across between soil and rock. So at one point, the female cataract was completely abraded, because the risk here was that you not only you have a hard rock alternating with soil, but you also have a risk of boulders. So in our case, a large boulder was found, and these photos were coming from the Tunnel Talk website. I happened to be on that job as well, so we had to build quickly a recovery shaft. We pushed the machine, thanks to the contractor ability, they were able to push the machine after the railways. You see, we were just under the railway when the accident started to happen. They pushed it after the railway so that we could have created a safe zone for the extraction of the cataract. And but on the same line, I spoke about boulders causing this damage. There are also situations in which a station excavation was considerably delayed because we found an ancient cannon. You see here now being hosted in a museum. So not only natural obstructions, but man-made obstructions should be remembered. And in this case, this one was interesting because was in this station, City Market, was built between the Tipu Palace and the Tipu Sultan Fort in Bangalore. For those of you who have visited the city, these are two of the biggest attractions. And we found out that the Sultan has built a tunnel in in 1700, right? Moving from his palace to his fort, because he had received some cannons and he needed to move ammunitions and cannons as the British were attacking the city. These were actually French-made cannons because the French were against the British in the war and were supporting everyone who was against the British. In this case, Sultan Tipu was against them. So unfortunately, that piece of history got lost. So when we studied the geology, we didn't have that piece of story, and we only rebuilt it afterwards as we found this canon, and archaeologists came and helped us understanding why that canon was in the middle of that land. So it just reminds me of some additional risks that we should consider. So I think this could be a good slide to include. I don't have to speak about this other case history, but why don't I just pull out conclusive slides here, which try to wrap up what I believe are the main lessons learned for me. Working in tunneling is really even simplifying that initial framework I gave you on the risks. This one really showed the technology, the contractual forms, the materials, and the geology being the major drivers, in my opinion, of the success or failure of a tunneling project. Technology is critical. Our supply chain is driving innovations every day and may affect a lot the time and the schedule. The contractual forms, as I mentioned before, the procurement method, how you engage the industry, how you distribute the risk between owner and contractor are essential, and they speak about the legal framework of a project. The geology and geotechnics needs to be known very well. I don't need to speak much about this because that's what we study, how to limit the type of risk in universities. And finally, the materials, not only the environmental carbon footprint, but also the direct cost, right? Like how we reduce them? How do we face the risk now of a very overloaded supply chain that still cannot pick up with the demand that we have across the world? So look at how we can do locally, how we can improve the materials, how we can reduce also the transportation and reuse what we excavate as much as we can. That's it from my end. I hope this is appropriate conclusion for this today's discussion.
Any other question? We can check for a minute. So if anyone having any other question,
you're muted.
just raise your hand. Yeah, I think there is no any other question. Hello, am I audible now?
I cannot hear you.
I think there is no such question. If anyone having any question, please raise your hand.
Can anyone hear what Mr. Cherny is saying?
Yes, we can.
Yes, I think. Okay, I think, sir, am I audible to you, sir?
I cannot. Mike, Sandeep,
Now,
I heard you before. Can you hear me?
Now you can remove your headphones, sir.
We can both hear you.
Yes, I see you guys are speaking. It's just me.
Yeah, I think.
Now you can hear me, sir.
Now I can hear you guys. Apologies. That
okay. So I think
so
there
you
is
heard
no.
nothing of what I said up to now, or you heard something?
I think there is no such question. If anyone having any question, please raise your hand. Just we'll wait for few seconds.
But you guys heard what I said about the Bangalore accident or not?
Yeah, it's nice, sir.
Okay, so it's just my audio was not working to
yeah, that's fine. Okay, before signing off, I would like to inform that all our past webinars are available on our TAIym YouTube channel. So you can go through the channel, and also very soon we will upload this webinar also in our YouTube channel. So I would also like request all member to renew their membership for this year 2023. And also the people who has not yet got any membership from TAIym, please contact us. And also I would like to invite all new members to get involved in various activity of TAIym. So once again, thanks, Mr. Gaspari, sir, for your wonderful presentation, for your wonderful presence and times. So thanks you lots for joining. All thanks you lots. Have a great weekend and safe and happy tunneling. Thank you.
Thanks, everyone.
Bye-bye.
Thank you very much. Bye.